These are Newton's laws of motion. We have inertia, F equals ma, and action-reaction. What we'll be working on over the next few days is dealing with inertia, an object's tendency to keep doing what it's already doing. Anytime an object has mass, it has inertia, and the more mass it has, the more inertia it has. Objects at rest stay at rest, objects in motion stay in motion unless acted upon by an outside force. That's true whether it's moving or not. The next part we'll be looking at is momentum, and that is when it is moving.
So the difference between forces and momentum, forces put things into motion and momentum keeps them in motion. And momentum is a measurement of moving inertia. For momentum, it has to be moving. And what we look at with a momentum is going to be equal to the mass of the object times the velocity. Momentum is kind of how much it wants to keep moving. So if it's really heavy or if it's moving faster, it will have more momentum. The way that we represent that in physics, first of all, momentum has the units of kilogram times meter per second. With acceleration, we use kilograms times meters per second squared, and we switch it to a Newton. With momentum, we don't do that. We just keep it as is. We just keep both of the units. Mass is still measured in kilograms. That means if something has grams, you have to convert it to kilograms first. And velocity is measured in meters per second. So there's no switching into something else. You just write both of the units for that. The way that it's represented, though, we know that mass is represented with an m. We know that velocity is represented with a v. And momentum makes no sense, and it's represented with a p. So anytime you see p, it's measuring momentum, and the units are kilogram times meters per second. It's different from newtons that are kilogram times meters per second squared. So when we're looking at momentum, these are the things that we have. An example that we have for that would be this. Example 1. 72 kilogram runner is going 7.5 meters per second. Find momentum. And yep, you can look at that and say, well, I'm just multiplying the two. But one of the things that happens with the 5 steps here is it's showing the physics behind it. It's showing that you know that this isn't mass and acceleration. You know that you're solving for momentum, not force, and those types of relationships. So we stick out the stuff that we have. We know that m is equal to 72 kilograms. We know that our velocity is 7.5 meters per second, and we know we're looking for p. We know that p equals mv, so we have 72 kilograms times 7.5 meters per second, and that's going to give us 540, and we just keep the units. Kilograms times meters per second. Nothing cancels, we don't change it into anything. But this tells us that you're looking at momentum, that you know you have velocity, that you know you have this, and you're not trying to do something with force or acceleration or newtons. So the 5 steps, while it probably isn't necessary just to know that to multiply 2 numbers, it still shows the physics that's involved in what's happening. The other part that we're looking at is this idea of impulse. An impulse happens when you're changing your velocity, and so you're changing your momentum. What happens with impulse is any change in momentum. Usually this is going to take place in the way that something is speeding up or something is slowing down. You can see an example like this if you're driving a car. If you have your car here and you're driving at 30 meters per second, and you're going to come to a stop here. Well, you can be driving and put on the brakes slowly. And you brake this whole amount of time till you come to a nice stop. Or We know that the stop is here, and maybe you don't notice that so quickly. So here's your car. You're still going 30 meters per second here. And now, you've got to do that real fast. So you have a longer time, but then you have less force. And you have a shorter time, but you can still stop. You just need more force. And so that's the idea of impulse. The equation that we use for impulse looks like this. You have a change in momentum is going to be equal to your force applied times the time it takes to stop. If you have a big force, you can have a little time, like you have here. If you have a little force, it'll just take a longer time. We write this like this. We say delta P is equal to F times T. Change in is the delta sign, momentum is the P, and then force and time. Anytime we calculate the change in something, we say mvf. You have what you started with, so your mass times your final velocity for your final momentum, minus your initial momentum. So what you started with here, what you're ending with, and it'll give you your force times your time. This is the equation that you'll get on the quiz. So it looks something like that. An example of this would look something like this. If we had example 2, a 900 kilogram car is going 18 meters per second. It stops in 8 seconds. So from 18 meters per second down to a stop at 0 meters per second in 8 seconds. Find force. So the way we would set this up, we know our mass here. We would say M equals 900 kilograms. We know that our VI, what we started at, is 18 meters per second. And our VF is 0 meters per second. And we have a time of 8 seconds, and we're going to solve for our force. So we want to know how much force it takes to stop that car in 8 seconds if it was going at 18 meters per second and it was 900 kilograms. So we'll take and we'll say mvf minus mvi equals force times time, and we're going to solve for the force, so we need to bring the time over. We'll divide by time, like that. So now we can put our numbers in there. We know that our mass is 900, but then we're going to multiply that by 0 because our VF is 0. That whole thing is going to go to 0. And then minus, again, still the 900, times our VI of 18 meters per second, divided by our time of 8 seconds. And when we do that, we get 5,025, and we're measuring a force, so that ends up being newtons.